let's work on writing power series. Let's start out with an example. So we're going to write power series. Let's start out with an example of, this is for a function or for functions, okay? My function, f of x, is equal to 3x minus 8 divided by 3x squared plus 5x minus 2. I want to center this at 0, so that will be called a Maclaurin series because it's centered at 0. But what I want to do is I want to write a power series for this. Now, one thing I notice is that this has a denominator that can be factored. So I could write this as 3x minus 8 over, and then factor this. I've got 3x here. I've got x here. I'm going to put plus 2 so I can get the plus 5, and I'm going to put minus 1. So that gives me 3x squared plus 6x minus 2. And I'm going to do partial fractions. I'm going to call this a over 3x minus 1 plus b over x plus 2. Now these are just linear factors, so I don't have to do anything special. Go ahead and multiply by the least common denominator. So 3x minus 1, x plus 2. And then this side, same thing, 3x minus 1, x plus 2. I end up here, 3x minus 8 is equal to a times, the 3x minus 1's cancel, x plus 2, plus b times, now I've got 3x minus 1 because the x plus 2's canceled. I want to let x equal minus 2. So let x equal minus 2. It's going to give me 3 times minus 2 is minus 6. Minus 8 is minus 14. And if x is negative 2, this is 0. I've got b. 3 times negative 2 is negative 6. Minus 1 is negative 7. So divide both sides by negative 7. Get b equals 2. Now if I let x equal something else, the easiest thing overall would be to let it equal 1/3. So I'm going to let it equal 1/3. 3 times 1/3 is 1. 1 minus 8 is negative 7. Then I have a times 1/3 plus 2. Okay, 1/3 plus 6/3 is 7/3. So put 1/3 here, we get 0, which that's great. If you go through and divide both sides or multiply both sides by 3/7, so let me do that. That will give us minus 3 is equal to, see this, a. So a is going to be negative 3. So we can set up our function like this. We can say that our original function, f of x, is equal to negative 3 over 3x minus 1 plus b is 2, over x plus 2. Now I want to make these look like geometric series. So here is the plan. I'm going to take these individually. So let's work with minus 3 over 3x minus 1 and make it geometric in style. Geometric series have solutions of a over 1 minus r. That's not supposed to be there. So this is similar to that. I need to swap it around a little bit because r is the part that gives us the convergence or divergence here. So I'm going to multiply the numerator and denominator of this by negative 1. So negative 1 here, negative 1 here. So what I end up with is 3. This is negative 1 times 3x, so negative 3x. Negative 1 times negative 1 is positive 1. And then I'm going to rewrite this as 3 over 1 minus 3x. Okay? So this is going to be my a over 1 minus r. Now, it's already centered at 0 because I have x by itself. So very easily relates there, and the 3 relates here. So the series for this piece is this. It is n equals 0 to infinity, and then ar to the n power. Geometric series have ar to the n power. So this would be a, which is 3, and then r is 3x. Notice it had the minus already, so this is 3x to the nth power. So there's a series for that fraction. Now this one, 2 over x plus 2, centered at 0 still. I'm going to swap these around. We can add in any order we want, so 2 plus x. Now I have got to have a 1 here for this model to fit, so I need to divide everything by 2. So let's divide by 2 here, here, and here. That will give us 1 over 1 plus x over 2. So this series, and I'm just going to add them together. I mean, they are part of the same function anyway, so I'm going to add this. I'm going to have the a part of this one, which is 1, times r to the n. So 1 times r is x over 2 to the nth power. So here's what we have. We've got this combination right here that equals this function. All right, let's try some other series. Another example that I would like to deal with is finding the Taylor series for cosine x, centered at pi over 2. Now that's an easy value for us. So let's see what happens. Okay, Taylor series. Taylor series is like Taylor polynomial, except it just goes forever and ever. So if you want to look at a definition, the terms in the Taylor series, they tend to be like this. Function f of x is equal to, and then it's got a constant. I'm going to call this a sub n, a sub 0 to start with, times x to the 0 over 0 factorial. And then the next one will be a sub 1, x to the first over 1 factorial. And then a sub 2, x to the second over 2 factorial, etc. Okay? A sub n, what is that? Well, that is a value, so a sub n is equal to the derivative, so the nth derivative, put it in parentheses so you read it as derivative, at the center. So you calculate at the center. Now, not only that, I don't have anything different than a 0 center right here. So generically speaking, we should do something about that. Let's say that this should be a sub 0, x minus c to the 0 over 0 factorial. And then a sub 1, x minus c to the first over 1 factorial, and so forth. Okay, same a sub n. What we need to do to get our cosine function centered at pi over 2 is we've got to find some derivatives. So if f of x equals cosine x, then f prime of x is equal to minus the sine of x, and f double prime of x is equal to the derivative of minus sine, which is minus cosine x, and f triple prime of x is equal to the derivative of minus cosine, which is sine. Then f fourth prime of x is equal to cosine, and this pattern starts over again. So what's the cosine of pi over 2? Well, it is 0. Minus the sine of pi over 2 is minus 1. Minus the cosine of pi over 2 is 0. The sine of pi over 2 is 1. The cosine of pi over 2 is 0. So you'll notice there's a pattern, and it's 0, 1, 0, 1, with the ones going from positive to negative occasionally. So let's set this series up. Our function, f of x, is going to be these as a values. So we've got 0 for the first one. So 0 times x to the 0 over 0 factorial. Then we're going to have a sub 1. That's minus 1. Then we're going to have x1 over 1 factorial. Then we're going to have, I don't have this centered, do I? X minus pi over 2, to the 0. X minus pi over 2 to the 0. Then here I'm going to have plus, the next term is 0. So this one was to the first power. So I'm going to have 0, then x minus pi over 2 to the second power over 2 factorial. Then I'm going to have plus 1 times x minus pi over 2 to the third over 3 factorial. And then I'm going to have a 0 again. So I kind of messed that up. Let me rewrite it. F of x, so this is continuing on forever. This is 0. 0 factorial by definition is equal to 1, so I'm not dividing by 0. But I've got 0, and I've got minus 1, and then x minus pi over 2, and it's over 1 factorial. And this one's 0, and I've got this one, plus 1, x minus pi over 2 to the third over 3 factorial. And I'm hoping that you can kind of start seeing a pattern, even though we've only got a couple here. Next one's going to be negative. These are all odd powers. So next one's going to be negative 1, x minus pi over 2 to the fifth over 5 factorial, and so forth. So, in general, we've got a series, n equals 0 to infinity. Okay, so how do we do this? How do we make it work? Well, minus 1, so we've got to have negative to start with, so we could go negative 1, go something like n plus 1, because it's going to oscillate, so we've got to have n there. We've got x minus pi over 2. Now, we want to go 1, 3, 5, 7, so forth, so we've got to say something like 2n plus 1. So when n is 1, we're going to have 2 times 1 plus 1 is 3. So the power will be 2n plus 1. And then it's divided by that same number, that 2n plus 1, but that's factorial. So there's your series for cosine centered at pi over 2.